Hello, everyone, and welcome to the next update in the CosmoPalooza 2023 series. My name is Anthony Cremeen. I'm one of the co-organizers, and I'll be the moderator of this session. We're happy to have Rubin and DESC here to talk about their ongoing project. So with that, please, Zilko, please take note.
Do you see my full screen?
Yes, it looks great. Please go ahead.
Excellent. Thank you for inviting Rubin team to give this brief update. As it happened, we are having scheduled workshop at the same time as this presentation. So I will not know some details until the end of the day, but I'll tell you what I have at this moment. Assuming there will be some new people who are not super familiar with Rubin, I will start with just brief introduction. And then I'll give you update on the construction, and I'll spend a few slides at the end to tell you what's remaining to be done and when can you expect the completion of Rubin construction and the moment that we all are waiting for, the beginning of the legacy survey of space and time. I will have some videos that I will not fully play. I assume that the slides will be linked later to CosmoPalooza website so that you can later see the full videos. Just briefly, our mission is to first to build the system, well understood system that is well calibrated and understood so we can all jump on science as soon as we start producing data. It will be an unprecedented data set, about 60 petabytes of images, and we will process these images to a point where we have catalogs of objects detected and measured. In our images, there will be both deep coets and time domain information. And we are developing software Rubin Science platform that will allow everyone around the world to easily detect these data sets and also to follow alerts that will be issued within 60 seconds of closing the shutter in Chile. And we also have extensive education public outreach program that will help everyone at large to explore the universe with us. Just brief comment on how does Rubin Observatory compare to some other fascinating ongoing projects that we have. So just like Hubble Space Telescope has two successors, James Webb Space Telescope, which has a larger mirror, but similar field of view. And then we have Roman Space Telescope that will be similar mirror to Hubble, but it will have much larger field of view, about 100 times larger. For the ground-based observatories, we have three large telescopes, ELT, TMT, and GMT, which are trying to go deeper, faster by having much larger mirrors. And then we have a complementary design. We have Rubin Observatory, where the idea is to have very large field of view on a decent telescope. So 8-meter telescope, it's not 30-meter, but it's much larger than telescopes that have been used previously for surveys. And because we will have 10 square degree field of view, we will be able to scan the whole sky within few nights and then repeat. So for 10 years, end up close to 1,000 observations of each point across half the sky that we can see from Chile. So the reason for this project, the reason it's funded and that the community excited about it is based on 4 science pillars. It is not that we think we will be doing only this science, it will be a survey machine, but those 4 science teams were used to quantitatively design the system and spec the system that we are building. In particular, cosmology plays a major role in justification of the system. So we will be doing cosmology with galaxies and supernovae. Supernovae will be enabled by our time domain data. And eventually, we think we will have simulations show that we will have enough statistical power to distinguish between GR and various modified gravity theories. We will be able to tell if the data are consistent with the hypothesis of dark energy, or perhaps we need to forget about dark energy and we need to modify gravity theory on the largest astronomical scales. One key point is that we will not carve the data set into these 4 different themes, but a single data set will be used to enable all these 4 science teams. So in particular, in the context of cosmological probes, we will be doing weak cleansing and galaxy clustering and BAO with galaxies. We will have about 20 billion galaxies in the sample. When you put signal-to-noise cut that enables precise measurements for cosmological purpose, we think we'll have about 4 to 5 billion galaxies with sufficiently accurate photometric redshifts, as well as shape measurements to enable weak cleansing. So essentially, we will not be measuring just the Hubble constant as a function of redshift, but we'll also be measuring growth of structure. And because those 2 functions can then distinguish predictions between modified gravity theories and standard GR with addition of dark energy, we will be able to make these measurements. For those who don't work with optical data every day, I just put a little comparison of 2 images, one which is 22nd magnitude depth, like SDSS, assuming everyone is familiar with SDSS. It's a very tiny image. It's about 3 by 3 arc minutes. It is 1/16 of our CCD. In the bottom right, you can see the outline of our camera with 189 science CCDs. It's about 10 square degrees area. And you can see 1 CCD outlined in red, and this image is 1/16 of that red area. So it's teeny tiny image, but contains lots of objects. Now, when you go 5 magnitudes deeper, like in this version, which was obtained with the Japanese HSC on Subaru telescope, you can see how deeper data allow you to see more objects. So I'll flip briefly between the 2. You can see why LSST will contain measurements for 20 billion galaxies. We simply go deeper. The observing strategy is based on automated code that has a cost-benefit function coded in. We have a very extensive program of interaction with community or communities. It's not just cosmology, it's the other communities. We think and we demonstrated with simulations, we can obtain data sets that will enable all these science programs. This is about 1,000 times faster than in real life. Each image takes about 30-second exposure, 40-second total, with slewing and settling and readout. So it's very fast readout, 2 seconds. And so later you can then look at this video if you want to see how it switches between the band passes. This big red line is galactic plane. The black line is horizon. So I'll leave that for later. So to summarize what Rubin is, it is a new observational system that includes telescope and LSST camera and lots of software. The goal is over 10 years to obtain about 60 petabytes worth of images. These images will be processed to produce catalogs for all objects. It will enable photometric redshifts for galaxies. We will have measurements of the shapes of galaxies, and there will be exquisite software system called Rubin Science Platform to enable LSST users around the world to do science with this dataset. The Rubin Science Platform will be delivering data products on different timescales. So alerts, which means all objects detected in image differences, will be reported within 60 seconds to everyone in the world. And then there will be data products that will be issued on 24-hour timescale. Then full images will be released after 80 hours. And finally, we will have yearly data releases like all other major surveys. The first year will have data release after obtaining 6 months of data, and later it will become yearly increments. Our education public outreach system is designed to speak to 4 different audiences. It's already completed. It was accepted. It's not part of construction program anymore. Now it's run by the Rubin operations team within Noir Lab, and they are already preparing to use extant data to demonstrate how to work with this system. So where are we now? We've been working on this project for about 20 years. It is very pleasing to see that some of the CAD/CAM designs that you can see in the top row for the observatory, for the telescope in the middle, for the camera on the right, is now becoming real physical objects. And the bottom row shows observatory as it is now in Chile. Weather looks a little bit worse than simulations, but it's not typical day. You can see telescope in the middle, and you can see one photograph of the integrated camera in its clean room at SLAC laboratory. So let's see, drone movie. We will skip this in interest of time. You can later click on it. You can see Cerro Pachón in Chile. The one in front is Rubin Observatory. And then you can see our neighbors, SOAR Telescope and Gemini South in the background. Telescope mount assembly was accepted. Let me see, how do I get that? Okay. It's designed to be very fast. Slew and settle time is 5 seconds. So we can acquire next field in very short amount of time. This is not sped up. This is the actual speed of the telescope mount assembly. That was during testing about half a year ago, maybe a little bit more. When it goes back, you can see a yellow cross at the bottom of the telescope where we are supposed to have primary mirror. This is not integrated yet, primary tertiary mirror. Here you can see itself, the black thing at the bottom of the telescope. That's the M1, M3 cell with several hundred pistons to control the figure, but it's still just mirror surrogate. And over the next few months, we will start integrating glass into the telescope. Here is photograph of the camera. It's already in the Guinness Book of Records as the largest astronomical camera ever assembled. It has 3,200 megapixels. Here is lens, entrance lens to the camera. You may remember from your high school that the largest lens ever produced was Yerkes telescope lens, but this is now 1.4 meters. It's larger than that one. It's, as far as we know, it's the largest lens ever produced. Here is a beautiful photograph of the focal plane. So there are 189 science sensors plus 12 in the corners that we will use for focal adjustments and for wavefront sensing. So the camera was assembled fully about a few months ago, and we were supposed to go through the final round of electro-optical testing. And indeed, it was supposed to be shipped in about a month from now to Chile. During that last round of testing, we discovered that there is a vacuum problem, that there is a tiny leak that prevents us from reaching the final vacuum at the level of like 1 millionth of atmospheric pressure. We spent last over a month studying in detail that leak and developing mitigation strategies. So next week, we are supposed to have notice to proceed and apply mitigation strategy to plug that hole. At this moment, we believe that that if that works, the camera should be cold and with vacuum and ready to undergo the last set of electro-optical testing by the end of this month. There will be some delays in shipment, and that workshop I mentioned earlier today is trying to re-optimize the sequence of activities at the summit so that we minimize delays to the end of construction because of the delay in shipment of the camera. We also have new data facility at SLAC, which is already operational. We have auxiliary telescope that we are using now to test software, to test data transfer, to test automated data processing at that facility at SLAC. There are 2 other facilities in UK and in France, which are also active. Here is one example of that early commissioning. So the big camera is still at SLAC, but we are already testing a lot of our software, essentially undergoing commissioning using the telescope. In particular, the image on the bottom left is what we affectionately call milli-kilo-degree survey. It's 1 degree of sky area that was obtained with many smaller images. The field of view of auxiliary telescope is much smaller. So that image is a composite of smaller images that we obtained with Oxtel. It demonstrates that our software for collecting data and for producing co-edit image across the whole sky is already operational and by and large debugged. So obvious question now is, are we done yet? When will LSST start? When are we going to start getting data from LSST? When are alerts coming online? When can we start studying the first supernovae discovered by the system. When is the first data release going to happen? So that was all supposed to happen before today, but there was a number of unplanned events that slowed us down. The most famous is COVID, of course. We lost close to 3 years due to COVID. And then there were smaller unplanned events that would take a month, 2, 3 months. It all adds up. So we are not done yet, but we have a very clear idea of what remains to be done. And very soon, once the camera is shipped from SLAC to Chile, we will be in position to produce much more reliable forecasts. So we are planning the remainder of work around 2 major events. One is called First Photon. The other one is System First Light. First Photon is after integration of the system, when we get the very first image of the sky with the big camera. And of course, at that point, we have to fine-tune the system. So we anticipate it will take us about 3 months to fine-tune the system and to arrive to what we call System First Light. First science quality images that will be shared with the world. And from that point on, we are going to complete commissioning by undertaking essentially science quality surveys, close to 2 months worth of data for comparison that will be similar to the entire data set collected by Dark Energy Survey. So that data set will be used to demonstrate that the system is operational, that requirements are met, and that we are in position to then start automated observing of the sky, to start legacy survey of space and time, run by the scheduler and algorithms that are built into that scheduler. So we don't know yet precisely, and by precisely, I mean, we can't tell you to within a few months precisely when that moment will be, but the uncertainties on our forecasts are steadily decreasing as we integrate more and more of the system. At this moment, we believe that System First Light with LSST CAM will likely happen around late 24, early 25, and we hope and we anticipate that LSST will start in 2025. You have to remember that it's impossible to predict future with precision better than a few months, but as we integrate more of the system, these uncertainties will go down. And the most important next milestone is to establish that LSST CAM operates as needed, and then we'll box it up and send to SLAC sometime early next calendar year. Details are TBD at that workshop today. So in a month or so, we will broadcast updated schedule and more precise dates. So to summarize, construction is going longer than expected, mostly due to major unplanned events. But so far, and that's important, everything that was accepted, all components within the system, they all meet technical requirements or they exceed them. So finally, once we get to the point of getting data, data will look as well as advertised. In some ways, it will be better than advertised. Bottom line, we hope to be done and a little bit under 2 years in 2025. And we also hope that commissioning will be successful to the point that we will be brave enough to say, everything looks great, let's turn the scheduler on and let's start the legacy survey of space and time. So I hope I didn't go over allocated time. I will stop now sharing and take a few questions.
You did perfect on time. Thank you very much. That was great. Are there any questions for the Rubin side? There's currently none in the Q&A. So you're saying you're having a planning meeting today to assess the new timeline?
Yes, regretfully, I cannot listen to desk talks, but I have to run back to that meeting. And then once we decide, hopefully by the end of the day, it takes few weeks to propagate all the decisions through the system. And we are publishing our forecasts publicly in monthly increments. So there is a webpage called ls.st/dates, where anyone can check our latest forecasts on monthly timescale.
Okay, thank you. I'm not seeing any questions at the moment. It was a really fantastic talk, so it may not be that surprising. I think you did a great job of presenting the telescope, the
I will
survey.
send you slides later once you have your website. I'll send slides and those movies.
There is one question that just came in. So what is the latest on the impact of satellite constellations on LSST?
That's a very interesting question. We could talk an hour about it. The short of it is that there are two types of impacts. We will lose some pixels due to trails. We already have software that can find those trails without any other information, then mask them. And the impact on just raw pixel count is still under 1%. So there will be some masks. It's comparable to diffraction spikes from stars. It's comparable to gaps between chips. So it's not catastrophic. And then in the context of cosmology, there is also issue of systematic errors. For example, there could be crosstalk, there could be other nonlinearities in measurements. So we are working with our desk colleagues to quantify to what extent those systematics would affect cosmological measurements. At this moment, we know it will be nuisance. We cannot ignore it, but we don't think it will be catastrophic. Now, that's all based on assumptions about the number of satellites, about their brightness distribution, how they will operate. So far with Starlink, we assumed 40 or 50,000 satellites, that they will continue doing brightness mitigation. We have a very good relationship with SpaceX and their engineers. But on the other hand, there are some new developments that we haven't modeled yet, like those Blue Walker giant satellites of 64 square meters. Fortunately, their number would not be as large as Starlink, but we need to model this. We need to assess it quantitatively. I hope that the fundamental conclusion, it will be nuisance, but not catastrophic impact, will still hold.
Okay. Is there any plan to try and steer the observing away from them, or is that not really possible when you get large numbers?
That's a good question. It depends on the number of satellites. So far, we have showed that if you have like 40, 50,000 Starlinks, you would not gain much. But if you have these giant Blue Walker satellites that would completely saturate the focal plane, their number would not be tens of thousands. Hopefully, it would be only hundreds at most. Those we would definitely try to avoid actively. And there is already conversation with satellite providers how to pass on up-to-date orbital information. We have the code, we have tools to take that information and to adjust what we are doing with the scheduler.
Very good, thank you. We have one other question. How long after the start of commissioning will the commissioning data become available in RSP?
Right, that's coupled with the operations team, so that part of the work will be done by early operations. We think, if I now do not misremember, that it will take about 3 to 5 months since we are done with science validation surveys. Then we will process those data, prepare data release. So I would say expect it roughly 6 months after start of LSST. We should definitely provide those results from commissioning, if for no other reason, for the fact that we need to then focus on data release 1 after getting 6 months worth of data of LSST. So that's roughly the timing. So I would say late 95, early 26, everybody should have access to those science validation surveys from the commissioning period.
Great, thank you very much. I think we should hand it off to Desk and to Nikki. Thank you very much, Zoko.
Thanks again for inviting me.
Yeah. Nikki, please take it away.
Thank you. Okay, you see my slides again?
Yes.
Great. Okay, hello everyone. So now we're moving on to some of the science cases with LSST data. And you already heard a bit about galaxy clustering, type 1a supernovae. I will talk about a very new science case to do cosmology, which is with strongly lensed supernovae. And so, yeah, my name is Nikki Arendse. I'm a postdoc at Stockholm University and co-convener of the strong lensing topical team within DESC. And DESC is the Dark Energy Science Collaboration, which focuses on anything to do with cosmology using LSST data. So some of our main topics are evolution of dark energy, the nature of dark matter, and the expansion rate of the universe. And gravitationally lensed supernovae can help us with 2 of these questions. But for today's talk, I will focus on how they can measure the expansion rate of the universe. And we need more of these measurements of the expansion rate because currently we have a tension between 2 types of methods to measure the present-day expansion rate, or the Hubble constant. So the first type of method uses the cosmic microwave background radiation by determining the distance between us and the CMB, and then using the cosmological model, we can determine the present-day expansion rate. The second one is the local method, which uses more nearby astrophysical objects like type 1a supernovae and Cepheids, and then by relating the distances and redshifts, we can also get the expansion rates. And usually this is done with a distance ladder to link the low redshift calibrations to the higher redshift data points. So the results from each of these methods are that the CMB, as carried out by the Planck team, gives a Hubble constant of 67.4, while local measurements from the Shoes team get a higher value of 73. And these 2 measurements are now in 5 sigma tension with each other, which is often referred to as the Hubble tension. But to know whether there's actually new physics or systematics behind this tension, we also need more independent measurements of the Hubble constant, which ideally would not depend on the distance ladder. And this is where gravitational lensing comes in. So gravitational lensing occurs when we, as observers, look at a massive galaxy or a galaxy cluster with a distance source behind it. And this galaxy can act as a lens and bend and magnify the light rays from the background source, such that we can see multiple images of the same object. And these images will also not appear simultaneously because the light rays travel a different geometrical and gravitational path. And when this background source is a variable source like a supernova or a quasar, then these variations in brightness will also arrive at different moments at the images, which allows us to measure this time delay. And this is done with monitoring campaigns where we look at the light curves and the offset between them to measure the time delay. And this time delay depends on the gravitational potential of the lens galaxy, but also on a ratio of distances between the observer, the lens, and the source, which is called the time delay distance. And this time delay distance is an absolute distance. So if we combine this with redshifts of the lens and the source, then we can use it to constrain the Hubble constant. And this method, called time delay cosmography, has already been carried out successfully with lensed quasars. So here you see results from the Holy Cow collaboration, where they combined 6 gravitationally lensed quasar systems to get a really precise measurement of the Hubble constant, which also agreed with the local measurements. But there are some challenges when it comes to using lensed quasars for cosmology. So it's difficult to really constrain the mass model of the lens galaxy. And they also require quite long monitoring, usually decades long, to really get the time delay right. So lensed supernovae offers some advantages over lensed quasars, especially when it comes to constraining the mass profile, because when the supernova fades away, we can conduct follow-up observations and study the lens and the host galaxy in more detail. And also when it's a type 1a supernova, then we can use the standardizable brightness to get constraints on the absolute magnification, which will also help in constraining the mass model. And additionally, lensed supernovae generally have shorter time delays than lensed quasars. So this also means that we don't have to monitor them for as long. And when this idea was first proposed of using gravitational time delays to measure the Hubble constant, this was already in 1964 by the Norwegian astrophysicist Sjur Refsdal, and he also proposed to do this with lensed supernovae. But it's quite difficult, of course, to find them because they fade away. So after his initial proposal, it would take another 50 years before we actually found the first multiply imaged lensed supernova. And this one was called Supernova Refsdal in his honor. And it was a really lucky and also special discovery because not only did we see 4 images here in 1.1 of the same supernova, but also another image of this supernova appeared 1 year later, exactly as predicted, in another image of the host galaxy in 1.2. So Supernova Refsdal allowed for the first Hubble constant measurement by lensed supernovae, which came out recently with a value of 66.6 and a 6% uncertainty. After Supernova Refsdal, we found 4 more lensed supernovae by galaxy clusters and also 2 supernovae lensed by single elliptical galaxies. So the sample is quite small, but so far we can say that when it comes to cosmology, the cluster scale lens supernovae seem to be limited by the complexity of the mass model of the cluster, while for the galaxy scale lens supernovae, they tend to have really short time delays. And of course, we need to discover many more of those. This is only really the beginning. We only found 7 of them so far, which also illustrates how difficult it is to identify them. But these numbers are about to change dramatically with the advance of the Vera-Rubin Observatory and the LSST survey. So initial predictions based on limiting magnitude cuts predict that we'll find several hundreds of lens supernovae a year, which is a huge increase of a few orders of magnitudes from the sample that we have now. But we wanted to know what the impact was of the full LSST observing strategy on lens supernova detections. And for this, we investigated for type 1a supernovae in a DESC project. So to do this, we simulated lens type 1a supernovae, also including microlensing from stars in the lens galaxy, and then we computed the light curves. Then for each of the light curves, we also used the simulated cadence from LSST and applied that to see whether the lens supernova would still be detectable or not. So putting it together, our results are that we expect to find around 44 lens type 1a supernovae a year with LSST. So these are really good numbers compared to the 7 that we have currently. But of course, not all of them will be useful for cosmology. We need to have long enough time delays to get a good relative precision on the measurements. So if we only consider lens supernovae with time delays of 10 days or more, then we'd still be left with around 26. Another thing that we need besides long time delays is follow-up observations, because we need, we need to map out the shape of the light curves better, and we also need high-resolution imaging to get the lens mass model. So for this, we also required that the lens supernovae should be detected early enough for us to trigger follow-up observations, and they should be bright enough for spectroscopic classification. So when we apply these additional criteria to our simulated detected lens supernova sample, we find that we are still left with around 10 objects per year. And then if we make some assumptions that we get sufficient follow-up to bring the uncertainties in the mass model and the time delays down to 5% each, then we would reach 1.5% precision in H0 in 2 years of LSST observations. Now, this is of course more of an upper limit because undoubtedly we will miss some of them and we won't get all the follow-up observations that we want. But it's still really promising for such a newly emerging probe. And one of the remaining challenges is really to make the identification process go as best as we can, to make sure that we don't miss any of the lens supernovae. So we really want to know, are our search methods that we have now good enough? And to help with this challenge, we started a joint effort with the Strong Lensing and the Dark Energy Science collaborations within LSST, which is the Strong Lensing Pipeline. And this is a really large project, so many people are involved here. I just highlighted a few here on the side. And our first task that we're focusing mostly on now is to make a simulation pipeline. So here the idea is that we want to create realistic simulations of these lens transients and then inject them into simulations and eventually LSST data so that we can test all the lens finders and cosmology methods that we have. And our vision here is that we're not going to pick between any of the lens finders, but then everyone can use their own lens finders such that we really get the strengths from each of these methods. Another thing we can do with simulations is to compare the properties of lensed and unlensed populations. So here I'm showing work from a PhD student in Stockholm, Anna Sagres-Caracedo, where she looked into the colors and the peak magnitudes of lensed and unlensed type 1a supernovae. And she found that you can partly distinguish them because lens supernovae will appear brighter at a certain redshift, so a certain color, than the unlensed ones. So to summarize, with the Vera-Rubin Observatory and some of the efforts that I outlined here in this talk, we expect to find around 44 lens type 1a supernovae a year. And this is so not even including core collapse supernovae, which will also be really useful and really important. And with this sample, we can get a really precise measurement of the Hubble constant. We can also learn more about substructures in lens galaxies, high redshift supernova physics, and lots of other things that we will discover along the way. Thank you so much.
Thank you very much. That was fantastic. Also want to applaud the beautiful visuals. That was really great.
Thank you so much.
Yeah. So if anyone has any questions, please post them in the Q&A. Yeah, someone said they love the videos. Do you need spectroscopic redshifts for the supernova or lensed galaxies? Are the current simulations just using photo-Z's for the source and lens? So yeah.
Yeah, we definitely need spectroscopic redshifts. In the beginning, we also, of course, need photo-Z's to get an estimate whether something is likely to be lensed. But then if we have a good candidate, we do need follow-up observations. And especially if we want to determine the Hubble constant and really use them for cosmology, then we definitely need to have the spectroscopic redshifts. But that is, in a sense, even if the supernova faded away already, then we can still get those afterwards with the follow-up.
And for your projections, do you assume sort of current day modeling techniques and errors in the modeling, or do you assume sort of incremental improvements?
For the lens modeling?
Yeah.
Yeah, now it's more a bit like an optimistic estimate that if we can get the right high resolution imaging to get 5% uncertainty in the mass model, of course, that's a bit optimistic. Maybe you'll get a bit less precise constraints, but that's also good. And this is only using this sort of gold sample that really satisfied all those criteria. But I also believe that if we use the full sample of lens supernovae, even the ones with not as precise constraints, if we combine all of them together, that will still add a bit of precision.
Great. Are there any other questions in the Q&A? Otherwise, we are actually at time. So thank you very much. That was great.
Thank you so much.
Yeah. John, could you share screen, please? Excellent. It looks great. Please.
Hi, thanks for having me. My name is John Franklin Crenshaw. I'm a PhD student at the University of Washington, and I'm here on behalf of the DESC PhotoZ working group. The PhotoZ group is one of the most active groups in DESC, so I don't have enough time to go over everything that's happening in PhotoZ right now. But I'm hoping to give you kind of an overview of a lot of the work that's going into making sure that LSST cosmology has the accurate PhotoZs we need to reach the precision we want. So of course, when we're doing cosmology, we need photo-Z's for all of our galaxies so that we can split them into tomographic bins so we can do tomographic clustering and weak lensing and 3x2 point analyses, which is important because, as you know, in cosmology, your z-axis, your redshift axis, is not only spatial, but it's also your time axis. So it's very important for understanding the evolution of the universe. And for stuff like weak lensing, what we need are these N of Z distributions, which are just the redshift distribution for galaxies that are in a certain redshift slice. But we also want accurate photo-Z estimates for individual objects, which we call P of Z distributions. And this is important for stuff like cluster finding, for galaxy evolution, and for supernova cosmology. So for example, here is some work in prep by Rebecca Chen, a Duke PhD student, on adding photo-Z's to the supernova analysis, which allows you to push to higher redshifts and get even more accurate cosmology. But the problem is that for most of our galaxies, we only have photometry, and we need a spectroscopic sample with spectroscopic redshifts in order to calibrate and train our methods to estimate redshifts for our photometric sample. And previous surveys, for example, the KID survey, have shown us how difficult this is to do, that algorithmic choices you make in your spectroscopic calibration can have dramatic impacts on your cosmology. So on the right here from Hildebrandt 2019, you can see S8 contours in brown, blue, and pink that all are the results of different choices for that spectroscopic calibration. And so you can see the tension with that little red contour from Planck, whether or not this S8 tension is real or less or stronger than we think, might depend on the way you're doing the spectroscopic calibration. We need to be really careful about this. And it's also difficult for individual galaxies as well. There's lots of degeneracies between redshift and dust, emission lines, IgM extinction, et cetera. So we've seen a lot of high redshift examples from JVST very recently for this, right? So here's an example from NIDU 2022. They have this galaxy, the image in the top right, and they didn't know, is this a quiescent galaxy at redshift 5 or a really bright star-forming galaxy at redshift 17? These are much higher redshifts than we're going to have to worry about for DESC cosmology. But these degeneracies exist at low redshift as well. It's something that we need to care about if we're going to get the precision on our cosmology that we're aiming for. And so the the way we're attacking this problem in DESC is to build this pipeline called Rail, which there's a full diagram here that we'll step through the next couple of slides. But the idea is our goal is to forward model so that we can quantify and mitigate all of these different sources of systematic errors, so we can develop new strategies and have essentially the right error bars on our cosmology contours at the end of the day. And so what we do is we start with some cosmological simulation, like the DC2 simulation from the DESC, and we use some generative model to generate a synthetic catalog. And then we take a subset of that synthetic catalog and apply some kind of biases. We call this degradation. And the idea is that we're going to have a smaller subset that represents our spectroscopic catalog that is not a good representation of what the photometric catalog looks like. It has different colors, different brightnesses, different properties than the photometric catalog we're aiming for, because these are the things that cause problem in photo Z estimation. Then we take our simulated spectroscopic catalog, our biased spectroscopic catalog, and use it to estimate the photo Z's and the N of Z's for our photometric samples. And then we can evaluate how well we did on this photo Z estimation, both at the level of photo Z estimates, but also propagate this down to our cosmology contours and see how did these algorithmic choices, how did these different biases impact our contours for sigma 8 or W or whatever science you want to extract from our catalog. So our generative model right now, we have two different versions. One is PGFlow, which is a Python package for normalizing flows that I developed. What's useful about PGFlow is that you're generating a catalog from a fully probabilistic model. That means that every galaxy in your catalog has a notion that you can call a true photo Z posterior. So that way you can estimate, you can evaluate your photo Z estimation for each individual galaxy on the full posterior, rather than just relying on the point estimate of the redshift, which is what has been done in the past. We also have full stellar synthesis models that have been implemented by Luca Tortorelli. He's a postdoc at Munich. So that you can simulate these catalogs at the SED level. You can tweak different parameters that control properties of the entire galaxy population. And you can look at how these things impact your photo Z estimation and how they might propagate to cosmology or galaxy evolution studies. To give you an idea of the kind of degradation we're doing, the kind of biases that we apply to our different samples. One is adding photometric errors and survey non-uniformity to our samples. So I work on this with Chinjun Kang, who's a UCL postdoc. So in the top left, you just see that that's a survey depth map for one of the LSST bands. So for example, you can see in the middle there that there's these bands of deeper and shallower segments of the survey. That's from the rolling cadence of LSST. And in the bottom right, those plots are the shift in the mean redshift bin that you estimate for these different source bins from your tomographic redshift bins as a function of the kind of local depth of that little patch of the sky. And so what we're seeing is that as you change the depth of these patches, if you don't account for that effect, from area to area, you'd have systematic offsets in what you think the mean redshift is. And that's something that we need to account for in our cosmology. Another one is modeling spectroscopic selection functions. This is worked on by Irene Moskowitz, who's at Rutgers, and Zheng Yang, who's at Bochum. And this allows us to simulate spectroscopic data sets that resemble the kind of spectroscopic data that we'll actually have in reality when we're calibrating LSST. And I briefly wanted to just show you some of the other important methodological improvements that have been worked on in the Photo Z group lately. You might know that our precursor surveys like KIDS and DS and HSC, self-organizing maps or SOMs are really popular methods for Photo Z calibration. And so Zhang and Benjamin Stolzner, who's also at Bochum, have been working on different methods for kind of leveling up the SOMs we use for Photo Z calibration, both using hierarchical clustering, which is kind of a smart way to kind of smooth over missing areas of color space, and also simulated annealing, which are ways that you can try to kind of redistribute your tomographic splits in a way that kind of minimizes the clustering signal between neighboring tomographic bends. Jan-Luca Vandenbosch is working on simulating cross-correlation calibration of photoses, given what we'll have in this next generation when we have large overlap between this giant, DESI spectroscopic survey analysis T, which is going to allow us to get more precise cross-correlation calibration that's ever been done before. So we're really hoping that this is going to allow us to reach those really small biases that we need to get the full LSST cosmology that we've promised. Benjamin Schultzner again is working on different parameterizations for our redshift distributions. So in previous surveys, it's really common to just have a mean redshift shift for each bin. So as you're fitting your cosmology, you have your fixed shapes of your tomographic bins, but you kind of allow them to kind of slowly shift around in redshift space to improve the fit to your cosmology. He's working on making this more flexible by replacing these with Gaussian mixture models, where you can actually allow your cosmological model to marginalize over the kind of positions and widths and relative heights of all these Gaussians that you're adding together. And so that allows you a really flexible parameterization that you can marginalize over when you fit your cosmology. And finally, TQ Zhang, who's a link framework scientist and research faculty at UPitt, he helped lead the PhotoZ analysis for HSC Year 3, their cosmology. And so he's using our pipeline to rerun the analysis on HSC to both as a test of our tools to see, can we reproduce what HSC has done, but also to see, can he improve the analysis from HSC? Because if you paid attention to that, you might know that their two highest redshift bins, which are not well calibrated from cross correlations, saw some biases with respect to what their best fit cosmology preferred. And so he's trying to see if he can kind of discover the source of that bias and maybe improve on it using our new tools. So this is just a slide showing you all the other people that I didn't have time to mention today, but we have a very active group and working very hard to make sure we deliver the photoses we need for DESC cosmology. Thanks.
Thank you very much, John. That was great. If anyone has any questions for John, please post them to the Q&A. Hopefully you can see the virtual round of applause coming up. So as far as the PhotoZ group goes, I guess, do you plan on continuing to improve these algorithms as the survey continues, or are you hoping to have sort of a finalized choice of method by the start of the survey?
Yeah, so we certainly do not have a finalized method yet. We think what we'll do, what I'm about to say is all very preliminary, but I think what's likely to happen is that for year 1 analysis, it's going to be pretty similar to the precursor surveys with a few small improvements, both as a realistic goal to set for year 1, but also as kind of a bridge that we can make a more direct comparison to what came before to make sure that our analysis looks consistent. And then for the next round after that, hopefully push out some of the more comprehensive changes to the whole analysis framework. Hopefully we'll learn a lot in that first year of what our data is telling us of what directions are most important to push in for new improvements.
Good, thanks. There are no other Q&A coming in, and it looks like we're at about time for switching over to Marina. So thank you again, John.
Thank you.
Marina, please take it away.
Hi. So, hi everyone. Can you hear me correctly?
Yes.
Yeah,
Yes.
I assume that you are. So thank you very much for the invitation. And today I will talk about the activities in the DESC Galaxy Cluster Working Group, and I'm presenting on their behalf. And that is towards cosmology with LSST galaxy clusters. So galaxy clusters are the most massive bound objects, in the universe. As you can see on the figure on the left, they are found at the intersection of filaments in the cosmic web, and they are the peaks of matter density fields. They are composed mainly of dark matter, about 80%, and 20% of gas and galaxies that interact all together. and they are a powerful probe of the growth of structure in the late universe. And in particular, if you look at their abundance per unit of mass, as is shown on the figure on the right, we see that this number depends on the cosmology. And here you have the two prediction for either WMAP or Planck set of parameters in orange and blue. So galaxy clusters are one of the main cosmological probe for the dark energy science collaboration. And you see here on the right some forecast for the 10-year survey, where we show the different probes and the combination of all of them. So the activities are organized in the working group and different topical teams on dedicated subjects. And there is a large number, so 213 people that are following the DESC cluster Slack channel. So only a subset of people are currently active within DESC projects. And the current conveners are Céline Combé and Yuan Wenzhen. So the basic idea behind cluster cosmology in the optical, just to give you a brief sketch. So first we go from the LSST photometric catalogs containing also the shape measurements. We then need to detect clusters, so determine their position, redshift, and richness, an observable that scales with the mass. We need to then measure their mass using weak lensing, and in particular the tangential shear signal. Then we compare that to theoretical prediction, and from that we can infer constraints on the cosmological parameters. However, that is only very simplified, and in practice we have every step will be hampered by a lot of systematics. So we'll not go in the details here, but just to name the more problematic one for cluster at the moment, it will affect the detection and the mass, and it concerns selection biases, projection effects, and halo triaxiality. And actually, we heard more about that during the Monday session. So in order to tackle, so we really need to tackle all these systematics to use at best the constraining power of the more than 100,000 clusters that will be detected in the LSST. So previous studies have highlighted the necessity to better understand the link between the true mass, the richness, and the lensing signal, and in order not to bias a cosmological constraint. This was highlighted in particular by the dark energy science collaboration, by the DS collaboration. And so from that, we know that we will need to really heavily rely on external data, both spectroscopic, but also multi-wavelength in the X-ray or SD, realistic simulated images and catalogs, and combination with other large-scale structure probes. And all of that while maintaining reproducibility, because it's going to be a 10-year survey, and also scalability, because we have a huge number of clusters. So our approach so far is to use well-tested and documented public codes, and to try to keep them as modular and flexible as possible. So there is no tool or method that are set in stone. We do a close development with other static probes, because we have the common, we use common tools, and we are affected by common systematics. And we also try to foster a collaborative and welcoming culture in the working group. So here you can see a sketch of the preliminary sketch of the cluster cosmology pipeline, going from the cluster finder to the cosmological constraints. And we decided for year one to focus on developing the pipeline for number counts and mass or lensing profiles. So the data vector construction and modeling is using cluster and large-scale structure specific software. And on the right, you can see that the red box are highlighting DESC softwares. And the theory and inference part is use DESC software that are used by also all the various probes. So currently we are working on the development of the missing parts and also making the connection between the different steps. So in the following, I will focus more on the data vector part. So regarding the photometric catalog, of course, we don't have LSST data yet. So we rely heavily on simulation, and in particular, that of the DESC Data Challenge 2, DC2. So that consists of a mock extragalactic catalog called CosmoDESC2, covering 440 square degrees up to a redshift of 3, and for which we also have lensing quantities obtained by ray tracing. That was then used to produce simulated images in all LSST bands that were processed with a Rubin pipeline. So we have also object catalogs. And here on the right, you have an example showing nice clusters in the 5 years, simulating 5 years of LSST data. So we also made a huge effort towards the validation of the simulation by comparing to real data. And in particular, for cluster properties, we included 11 tests. So looking at the cluster member color, luminosity, distribution, with lensing signal, and so on. So that showed us that the cluster properties were overall representative of the real data, but we also identified some limitation, for instance, concerning the lensing at low scale. So that was then improved in the new mock extragalactic catalog called SkySim 5000. So concerning the cluster detection, we have 4 different cluster finder algorithms that were applied to the DC2 simulation. So 3 are the Red Mapper, WASP, and Amico that all works at the catalog level and identify clusters at other density of galaxies, either using the photometric redshift or the color information. So all of them were used in a previous survey. And we also have YOLO that is using a different approach where the detection is made at image level using a machine learning technique. And here on the right, you have an example of a detected cluster in the DC2 simulation. So by comparing to the truth, so the CosmoDESC2 simulation, we were able to assess the performances of the algorithm. So indeed, we have more than 450,000 massive halos in the catalog, and we were able to match them using to the detection using a dedicated depth software that is called Clever. So that allows us to have an idea of the selection function, the mass observable relation, and the centering efficiency for the different cluster finder. And here on the bottom, you have on the left an example of the completeness of the Red Mapper CosmoDESC2 sample as a function of mass and redshift. And on the right, you have the mass richness relation for the WASP CosmoDESC2 sample. So we are working at the moment on making the comparison between the different catalogs and detection algorithm. Concerning the measurement of the mass, we developed a DESC library for the galaxy cluster mass reconstruction from weak lensing observable. So that is called CLMM. The code is fully public and also tested and validated with mock data. We allow different modeling backends, so either CCL, NUMOCOSMO, or cluster toolkits, and also different lensing observables, so shear, but also magnification. So there are ongoing projects using the CLMM. So one is to link it to other DESC tools. So for instance, TakeSpipe, that is a 3 times 2 point pipeline, or QP, that is regarding the photometric redshift. We are also working on applying it to real data for individual clusters and developing the triaxial halo modeling. Finally, we are also testing the impact of source blending on the lensing profile. And very rapidly, just to show you some results, we did an exercise of trying to construct idealized data vector from the CosmoDESC2 and to model it during the DESC tools. So on the left here, you have on the top the Red Mapper cluster counts in richness and redshift bins, and that accounts also for the purity and completeness of the catalog. And on the bottom, you have the lensing profiles, so using true shape and true redshifts that were then used to fit the mass observable relation and some cosmological parameters here, sigma 8 and omega m. So that exercise allows us to test the pipeline elements and identify difficulties, for instance, regarding numerical integration. So to summarize, we use the LSST DC2 simulation to characterize cluster finder algorithm. There is an ongoing effort to build the cluster cosmology pipeline using the DESC tool. We focus on the classical analysis, so number counts and stack lensing profiles at the moment. and trying to keep a modular approach in close development with other static probes. We have a clear roadmap towards year 1 data, so stay tuned for further results. So thank you for your attention.
Thank you very much. We do have time for one question, and there is one in the Q&A. So it says, how are you going to estimate the completeness of member clusters of the member cluster sample? Sorry, let me repeat. How do you?
Yeah, no,
I
did not understand.
Estimate the completeness of the member cluster sample.
So I did not understand if we are talking about the completeness of the cluster sample or the cluster members. So for the cluster sample, for now we use the simulation, but we will try to have other techniques. So for instance, trying to inject fake cluster inside LSST images. So it's something we are also considering for the year 1. Probably we will have to also include that as in our fits, the model for the completeness and purity. Regarding cluster members, we don't have a dedicated plan so far that I can think of. So it will be important, for instance, to correlate that with spectroscopic data to have an assessment of the projection effects and also the completeness of the cluster members.
Great, thank you. And actually, we do have one more. So how do you address projection effects for LSST cluster cosmology?
Yes, so well, at the moment we are not there yet. So we are trying to first develop a pipeline that can do number counts and stack profile, as I said, using this classical analysis. Then there is a lot of interesting routes that have been explored in a previous survey and that was discussed on Monday. So this is why we say that we try to be as modular as possible, because we will integrate all of these new techniques. So there are projects using emulators, for instance. In our simulation, we have access to the triaxial components. So it's something we are also working on from our simulation at the moment. And
Great.
probably also a correlation with other large-scale structure probes.
Perfect. Thank you so much. I want to thank everyone, and especially the speakers for Rubin and the Dark Energy Science collaboration for their talks today. And thank you all for joining. That will wrap it up for today. Thank you very much.